So if you keep improving your errors step by step, you will eventually lead up to becoming perfect. And this thing is not just true for real life, this is also true for machine learning algorithms. Hey everyone, welcome to a Real Data Science channel. My name is Shubhankit, and in this video we will be understanding about gradient boosting algorithm. So this is a part 2 of this series of ensemble models. In the part 1 we understood about in general idea of ensemble models and what are bagging models, that are first category of ensemble models. Today we'll understand about gradient boosting algorithm, we'll understand about XGboost, which will give you a complete idea about how boosting algorithm works, why they are so good, right? What is the reason that they are so good? And yeah, this is an again a real data science channel. Here we talk about more generalistic approach towards data science. We want about models to generalize, we don't want them to memorize, and that is why our learning should also be generalized and not memorized. That is my thinking. And let's not waste much time. Just one reminder that in the part 2 of this video of boosting algorithms, if you are new to this channel, just visit the part 1, which was on bagging algorithms, and then you can continue with the part 2. So yeah, let's check this out, and let's not waste much time and dive directly to the video. So let's talk about boosting algorithm, guys, what they are and how they work. So here you can see I have just written down the complete outline of this video, okay, how we will move ahead in this video. So we'll just recap for the part 1 first, not the complete recap, just an overview, so that you can understand the flow of this series. Then we'll understand about boosting algorithms and intuition and the simple architecture of boosting algorithms. Then we'll go towards GBM, and then we'll go towards XGboost and what are its advantage over GBM, right? Before moving ahead, let me tell you, boosting algorithms are one of the most used techniques. I have said this multiple times that the ensemble models are one of the most used technique, and inside ensemble models, boosting algorithms are one of the most used techniques when it comes to solving actual industry problems. Okay, so most of the time, if you are getting problem in your models, you will end up using AdaBoost or XGboost or CatBoost. That will give you the best solution out there. So let's just dive into it. Let me just make a new slide, and let me give you a quick recap of what we did in the last class, right? So we understood about ensemble model. So ensemble models, as we said, work on an idea of wisdom of crowd, as you guys have seen on the thumbnail of this video, right? Wisdom of crowd. And the idea is that when instead of using one specialist model, you can use multiple weak learners, right? This concept of weak learners is really important. You can use multiple weak learners, and then you can take decisions out of it as a collaborative idea, right? So then there are two types of ensemble models. One in which they have model in parallel, other in which they have model in series. In the last class we understood the ones that are in parallel. So what we have in parallel, they are called bagging models, right? Bagging models, so basically they have multiple models in a parallel sequence, and once you pass the data there, so they will collectively give you an answer each. So for example, if it's a binary classification problem, each of them, let's say, gives you 0 and last one gives 1. So then you take a majority decisions out of it, and similarly in case of regression problem, you will be taking mean or median out of it, right? That was the idea of parallel algorithms, and that was bagging algorithms. Now in this video we are talking about series algorithm, and the example of them are boosting algorithm. So as the name suggests, you are boosting your models, right? So what happens in boosting algorithm, and now we are talking about the general idea of boosting algorithm. So general idea and architecture, right? The general idea of boosting algorithm is that you have one model. Let's say this model is called M1, and this model will train on your data, and it will collectively, let's say it's a classification problem and you have 100 rows there, and out of these 100 rows, model is able to correctly identify, let's say, 80 of the rows correctly, right? It's performing good on the 80 rows of data set, right? So I will make a second model that will be specialized to work on the leftover 20 data points, right, on which the first model was not performing good, right? So M2 will specifically work on the errors of M1 or a residual of M1, right? Similarly, we'll have a M3 model. Let's say out of these 20, M2 was able to classify let's say 16, and 4 were still left, right? So M3 will work on these 4 part, which was the error of M2, on which M2 did not perform really good. It's like that. So what you observe here is that M2 is boosting the performance of M1, M3 is boosting the performance of M2, right? So it's like improving over each other. And as I said in the introduction of the video, if you try to remove the error step by step, you will eventually lead up to a perfect model, right? That is an idea, and that is why it's highly used. That is why it is really good performing models out there in industry when it comes to actual use cases, because in actual case use cases your data is complex, right? And there your simple models like logistic regression, linear regression, decision tree, they don't fit, right? So in that case you want to have a model that are specialized enough, right? So these kind of models work there. So this is a general idea of boosting model, nothing much serious out there. Only thing that you have to remember is how do we carry the error, right? So I said, right, M2 is working on the error of M1, M3 is working on the error of M2, but how is that error getting carried up, like carried to the next model? It get carried by the help of residual. Residual, nothing, just a fancy term for error. So if your actual value is y and your predicted value is y hat, so your residual will be y minus y hat, right? This will be a residual. It is represented by r, right? This will be a residual value. That's a fancy name for error, right? Nothing else. And don't get confused here. You will get a residual in case of classification as well, and in case of regression as well. Even in case of classifications, you initially get an error in a continuous variable, and then you use functions like sigmoid functions to convert those errors into probabilities, right? And on the basis of that you can get a class of 0 or 1, right? So answer of a machine learning model is anyway a continuous variable when you convert it into a categorical variable. So don't get confused here, okay, how this residual will be calculated in case of classification error. We should calculate accuracy, precision or recall there. No, the residual will be calculated there as well. Now let's look at GPM. Okay, so now we have discussed, okay, residual is carried to next model. We have established this thing. Okay, now how this thing happens, how is this residual getting carried away to a next model? Let's look at that into. Okay, so now I'll define some terms here, right? So just stay with me and be patient about this. So we have our data as xi, right? So this is xi, and I'm saying xi, it's a bunch of features. Let's say some matrix of data, right? So you have basically features of data with xi, right? And your actual value here is yi. Okay, this is your actual value, the actual value that is out there. It's a supervised learning model. You will have a target label. Okay, so what you do, you try to fit your first weak learner, and let's call that f of x. So when you try to fit a data, you will try to basically fit a function on your model, right? So you try to fit the first weak learner f of x on this xi yi data. Okay, you will try to do that, and yeah, it worked, right? So you have a model f of x that works on x and y, but fx is a weak learner, so it will not perfectly fit your data. And that is the idea. We are using weak learners here because ensemble model help us to get a better accuracy without increasing the complexity of a model, right? So you will be using weak learners so that they don't overfit, but still you can get a better accuracy or better response from your models, right? So going ahead, you will get f of x here, and you will get some residual as well, right? You will get some residual out here as well, and let that residual be r let the residual be r1i. Okay, r1i basically means that residual for each value. Here I is my representation of number of data that I have. Let's say I have 100 rows of data, so I will range from 1 to 100. Okay, so for each data I have this model f of x, and for each data point I will get some residual, and as we have discussed, residual will be difference of actual value and predicted value. Now for each data I am getting this residual of r1i. Okay, next what I will do, I will train a model on this R1i and xi. I will train a model on this, right, and I will get a function out of that. Just like we got f of x, we'll get another function, and let's call that function h1 of x. Why 1 of x? Because getting from first residual model, just a representation. Let's call this model h1 of x. Okay, and this model basically is trained on the residual value and the feature value, right? So this model has an information. If you just look at from an intuition point of view, this model is trained on the residual value and xi. So for this model, ri was a target variable for h1. Ri was a target variable, right? So this model is trained on residual value and feature value. So this has an information on which data point has more residual, right? So this model has information on which data point has more residual, or in easy term you can say this model has an information of on which particular data point f of x does not performed good enough, right? So it has that information, right? So what we'll do as a next step, we'll modify our model. So till now our model was f of x. Now our model, and I'm making this bold m, right? So just understand it like this is the final model. So I'll update my model. Now my model is f of x plus h dash of x, right? This is my updated model after this step, right? Now once I've had this model f of x plus h dash of x, right, now what I'll do, I'll again calculate my residual. Again calculating residual means that I'll again bring up some new data point and I'll find the R2i. R2i is basically a residual value that we'll get after we'll compare the actual value yi with the predicted value of this modified model of the second layer, you can say. Okay, now again I have residual R2i. What I will do, I will train R2i with xi, original feature value, and this will give me a new function that will be my h2x, right? This will be my h2x. And now what I will do, as you have guessed probably, that I will again modify my model f of x plus h1 of x plus h2 of x, and you can just add a parameter here as well that talks about the weightage of each residual values, right? So this is the general process, right guys? This is a general process, and try to understand what is happening in the first layer. Let's say this is called the first layer is not the right word, but let's call the first step. Okay, this was the first step, sorry, this was the second step, and this was a third step. Okay, what is happening in the third step? In the third step we are calculating residuals, right, from the actual and predicted value of the second step. So when I say predicted value of a second step, it is coming from this model, right? So it's checking which particular data point my model has not performed good on a second step, right? So when I talk about this h2 model that is trained on the residual of the second step and original features, when I talk about this h2 model, this basically contains info on which data points were having higher residual till second step, right? So I'm collecting that information in this h2x and I'm adding that h2x to my final model, right? And this series, this series will continue, guys. The series will continue, and eventually you will end up with a model that is actually a good model where you are having really low residual from the previous step, right? And that is the point you stop, right? So this is an idea of boosting, and here what you're doing, you're boosting gradient. So gradient in this case is residual, right? So you're boosting your gradient in each step, and this is your gradient boosting mechanism or gradient boosting technique, whatever you want to say, right? That you are taking the data and you're doing it step by step. And don't worry, when you apply this code, when I apply the code for this, you don't have to write these things step by step manually. You just have to apply a function of GBM from SQL library and it will do the things for you. But this is a really important step, guys. A lot of people out there don't know about boosting algorithm, how they work. They only know about they work in series, they work in they improve over each other. But how they improve over each other, if that question comes up and if you explain it like this, you won't face any other counter questions from the interview. Now let's talk about what is XGboost then. So this was your GBM, okay, gradient boosting mechanism. Now let's talk about what is XGboost then. So first of all, XGboost is just a short form for extreme gradient boosting, right? So whatever we have studied in gradient boosting, same thing happens in XGboost. Ditto, same thing happens. Just there is one additional parameters that are added, right? And those parameters those are added is that first of all, this f of x, this model function that you are creating, that has multiple something like that, gamma 1 h1 of x plus gamma 2 h2 of x, right? Like this will have one additional parameters of regularization here. Guys, if you guys remember regularization, what we do in regularization, we have L1 and L2 regulation, lasso and ridge, which help us control overfitting, right? So in case of GBM, you can also add regularization, right? But in case of XGboost, this regularization parameter is inbuilt in XGboost, right? So you have both your L1 and L2 regularization inbuilt in the XGboost algorithm, and when you're using it, you just have to pass the parameters for parameters of L1 and L2, the regulation parameter that you have to pass, right? So that is one advantage, right? That XGboost is a gradient boosting algorithm with several advantages, and the one advantage is that it has regularization inbuilt in it. The second advantage is that it has cross validation also built in it, right? So when you apply it, you can apply cross validation directly. But these are kind of a code wise advantage, I would say. The major advantage that XGboost had, this works in parallel processing. So when you apply XGboost, this works in parallel processing. So compared to GBM, because GBM is a hectic algorithm, it takes time to run. If you have a larger data, it will take even more time to run, right? So compared to XGboost, compared to GBM, XGboost runs in a parallel process. And if you guys know, when a process run in a parallel process is run faster, right? So XGboost, because of running in parallel process, is faster, right? That is another advantage. And the last advantage is that it handles missing value by itself. So XGboost have advantages in itself where it identifies, okay, if there is a missing value in data, what should be the ideal value to replace that missing value. And that again is a really good advantage, because handling missing value itself in it quite a big topic, right? So that becomes the additional advantage in XGboost of how do we handle missing data there. So yeah, all of these points in XGboost are so if someone asks you about XGboost, you have to explain the same thing that we have in GBM. There are just several advantages of that, because XGboost by name is extreme gradient boosting, right? So it basically means that it's GBM but with several advantages, and then you'll have to explain the advantages. Okay, it has regularization inbuilt in it, it has cross validation inbuilt in it, it is works in parallel processing, so it's faster, and it has its own module, right? So if you are working with GBM, you will be using sklearn, right, library to import GBM. But if you're working with XGboost, you will be using XGboost directly. So you will be doing something like pip install XGboost and directly use XGboost instead of using XGboost from scikit-learn, right? So that is why it has several advantages, that it has its built-in cross validation, it has its built-in regularization, right? Just a code-wise example, code-wise advantages. There are other advantages as well, that you can apply a maximum depth parameter here, which you cannot apply in GBM, right? So you can control it more. But all in all, it's an extreme gradient boosting algorithm. So it's a modified version of gradient boosting algorithm, right? So that is the thing, right? That if boosting is asked from you, you have to explain gradient boosting, and then you have to explain the advantage of XGboost over gradient boosting, which is just the advanced way of gradient boosting, right? Nothing else. So yeah, I think that covers everything that we thought of covering in this video. Let me just recap with the list ones. Yeah, most of the topics are covered here. So yeah, this video was just to cover everything up for you for interview point of view, right? So application of this, code of this could be found anywhere, right? There's no point of me writing the code for you, that is already out there step by step, so I have skipped that part. So applying XGboost is also easy. It's not like different from any other model, and the days of AI writing code has becoming a lot easy, on better IDs are there, better tools are there that can help you write the code. So concept wise becomes really important, and because XGboost is highly used in industry, all the ensemble models are highly used in industry, it is really important to know the fundamentals behind them, right? So that was all I had for this video. Again, please prepare this thing properly. Interview wise, ensemble models are really important, and do let me know if you have any other doubts on which you want a video or something, or on which you want explanation or something. If you have any doubts in this video, please post that out in a comment of this video so I can answer them. My name is Shumankit. I work at Worldwide Technology as a machine learning engineer, and along with that I also prepare content over LinkedIn, over YouTube, over Instagram. I teach data science as well. You can ask me about that on my LinkedIn. And yeah, till then, just keep learning, and be patient if you're searching for a job, and good things will happen for you because you're searching properly. And yeah, happy learning. Thank you.